Hello, this is Mike Newtown. I am the Need of Engineering Technology at SUNY Canton, and I would like to talk to everyone today about heat pumps. It's a understanding of how they work for the general public. There's a lot of technical stuff that goes on with heat pumps, and I'm going to try my best to keep it really simple. So without any further delay, let's get into going over heat pumps. What's a heat pump? Well, as you can read there, it's a device that we use to move energy from one place to another. It has the advantage that we use refrigeration as the means of making the energy transfer from a warm environment to a different environment, whether it's hot or cold. Um, so generally, let's keep it simple for this slide, but if it's air conditioning, we take the heat out of the house and we want to send it outside. The interesting thing here is in the summertime, it's usually warmer outside than it is inside. So in order to do that, the refrigeration cycle gives us the advantage of making the energy transfer from one temperature to a higher temperature by the process of the refrigeration cycle and using some laws of thermodynamics to do that with. So it does cost us some electricity. Generally, that's not a bad thing, and it isn't going to be that expensive. But ideally, it's just a matter of moving heat from one place to another. I want to get it out of the building and get it outside. Or in the wintertime, I want to take some heat from outdoors and move it inside to cause some heating. That one's going to plague a few people to start with, so don't panic. We will talk about that in further detail. Whoops, and slide down here. Okay, so how do we make energy move? Well, hot always travels to cold. It's just a process in nature, and it's one of the major advantages that makes a heat pump work. And I give you an example here. So most modern heat pumps are using refrigerant R410A. There's some really detailed technical information on the refrigerant that we use, but let's say it's for right now to keep this simple. This is one of the safest refrigerants we have, although you will find that in a few years we're going to be changing to some different refrigerants. But for right now, R410A is what most systems are using, and we're going to play with this. So refrigeration is a process of using a chemical that changes state. And as it changes state, it absorbs the energy from its surroundings. A good example of this is if you take rubbing alcohol and put it on the back of your hand, it will evaporate, and when it does, it's causing a cooling effect on your skin. Well, the energy from your skin is causing that to evaporate. As it evaporates, it gives you that cooling effect. Okay, so that being said, R410A has a boiling point of minus 27 degrees Fahrenheit when we're at one standard atmosphere, which is 14.7 psi at sea level. We'll play with it at sea level, even though most of northern New York is about 400 to, depends if you're up in the Adirondacks, you could be as high as 1,800 feet. So depending where you are, but we're going to play with sea level for the time being. Give you a comparison of what this actually means. If you've ever boiled water, you have realized that it's about 212 degrees Fahrenheit when it's boiling off at standard atmosphere 14.7 psi. That's pounds per square inch. Okay. The ability of refrigerants to boil off, or in the terms of refrigeration systems, we talk about evaporating, turning from a liquid to a vapor, is what allows us to pick up the heat and move it from one place to another. Okay, and that is the beauty of a refrigeration system, and that is the heart of the thermodynamic principles of a heat pump. The ability for refrigerants to absorb energy from an environment, even though it would be seemingly cold to us, is relatively warm to it. So, as we stated here, so our 410A will boil off at 27 degrees below zero Fahrenheit. But if we're operating at 20 degrees Fahrenheit, we literally have a 47-degree temperature difference between the state of the refrigerant being a vapor and a liquid. That is 47 degrees of heat that we can add to the refrigerant to cause it to evaporate or change from a liquid state to a vapor state. And when we do that, we're picking up energy. Then we're just going to move it. Okay, we're going to use a compressor to move it from place to place, and then we're going to have a condenser that's going to reject the heat out of the system. Talk about a little more of that coming up. All right, so let's talk about how this actually works for summer months. Most people understand the need for air conditioning. So for cooling, we gather the energy from indoors and we push it outside. Thus, we get cooling or an air conditioning process. In the winter, we reverse that process and we can add heat back to the system. Now, let's play with this for a minute here, and I want you to think about summertime and air conditioning. It is, well, let's call it 80 degrees indoors, it's 95 degrees outdoors, and we got a high humidity level. So the advantage of this of an air conditioning system is it takes the heat from the indoor, which is the 80 degrees that you can measure for sensible heat. And by the way, sensible heat is the temperature that you can feel basically in your skin, that sort of stuff. And it also takes some energy from the latent heat or the hidden energy. That's the one that causes us the humidity and a few other things that we don't like with 80-degree weather and high humidity levels. Okay, and we can absorb all that energy through from the air through the copper pipe in the evaporator coil to the liquid refrigerant and send it over to the compressor, which then squeezes it from low pressure, low temperature to a higher pressure at a higher temperature. And there's some thermodynamic rules that go along with that. But basically, keep it as simple as possible. A gas, when it is compressed, increases its temperature. So we're going to take it out of the compressor and we're going to move it to a higher temperature. Say it's 110 degrees Fahrenheit, and when the compressor gets done with it, that goes to the condenser unit, and the condenser unit is going to have refrigerant that's in a vapor at 110 degrees. The outside air is 95. Well, there's a 15-degree temperature difference between the temperature of the refrigerant vapor and the air outside. Therefore, hot travels to cold, and we reject it outdoors. We cool the indoors. We take that extra waste heat that we don't want and send it outside and give it to Mother Nature again and give it back to her. Okay. Little side note here, as long as you're here, that's why it's important to have a well-insulated, air-sealed house. And there's a lot of rules that go with that, and we'll spend some time talking about that in another set of videos on building performance and the building science of making houses efficient. Okay, so save that for another topic, but just keep that in mind. All right, so in order to do the refrigeration process, we got to have a couple heat exchangers in this system. So we have one that's called the evaporator. That's the one where the liquid refrigerant at a low pressure is evaporated to a slightly warmer temperature. That goes to the other one, which is the condenser coil. And that coil rejects the heat into another spot, usually with much warmer temperature. Okay. We also need a compressor. I said that the rules of thermodynamics and how we get refrigerants to boil is the heart of the thermodynamics. Well, the compressor is actually the physical heart of a refrigeration system. It needs to take in a vapor and it squeezes it into smaller packets of refrigerant and adds heat to it and raises it in temperature and sends it to the condenser unit, and the condenser rejects it. Then we also need to have a metering device, which then, after the refrigerant's left the condenser and rejected all its heat it can, that it returns back to a lower pressure, lower temperature vapor. Okay, and those are the four major components of a refrigeration system. Now, when we go the other way, we have to add in a reversing valve, which is what causes the evaporator to switch places with the condenser, and the condenser becomes the indoor unit during the heating season or the wintertime. And the evaporator is the outdoor coil that's picking up the energy from the 20-degree Fahrenheit air, or even down to minus 20. Okay, the heat pumps do work pretty well down to minus 20, and even with my own experience, I've pushed it even to down to minus 27. There's some efficiency things there, and I have plans for another set of videos with some real data that discusses the efficiency of heat pump systems. Okay. Anyways, so generally we move heat from hot to cold, or if you want to think about it, inside to outside, as long as we can create a temperature difference in doing so. All right, so to give you a visual here, I found this image off the Adobe stock, and it is the simplest way to take a look at a refrigeration system. So remember, I said the compressor is the physical heart of the system, and its goal is to take take a vapor refrigerant at low temperature, increase its temperature, and squeeze it down into smaller packets of vapor and send it to the condenser where it can reject the heat. Condenser then rejects the heat and returns to a liquid state, but it's at a higher temperature until it goes through the expansion valve or a metering device, which then turns it back to a liquid, and then back to the evaporator where the liquid then becomes superheated vapor again at a low temperature, and works our way around. Okay, so if you want to play with some numbers here just to think about it, R410A on the evaporator when it's a gas or a vapor will be about 40 degrees. When it goes over to the other side of the compressor, it'll be about 110, and it's going to reject that heat out through the system and then back around and start a whole process over again. It just continually cycles that way. Now, the real big thing that goes on in here, so the expansion valve is probably the brains of a refrigeration system. But in order to protect the compressor so that it only gets vapor when we switch from cooling mode in the summertime to heating mode in the wintertime, is we need a reversing valve in there. And that reversing valve is the one piece that actually makes the whole thing work, to be able to switch to the evaporator coil with the condenser coil. Okay. All right, let's talk about the parts of a heat pump. So we have two major parts. We used to call these the evaporator coil and the condenser coil, or the condenser unit. But in the better terms of heat pumps and the things that go on with it, we're going to call them indoor units. Sometimes they're also referred to as the cassettes, where we are delivering the desired heating or cooling to the indoor space. Okay. The outdoor unit is now referred to as an inverter. And it gets the name inverter because it uses some special electronics to invert a AC signal to a DC signal, and then from a DC signal back to a modified, I don't want to say fake, modified AC circuit, but at a different frequency. Okay, so the inverter provides us the ability to take AC current at um, at 60 hertz, all right, and play around with the frequency that we're moving the pump or the compressor to move the refrigerant. So if we turn it into a digital signal, then we can do simulated AC with DC pulse um, to drive the compressor. I'm going to skip from there on to the next slide because that's going to get a little complicated, and I'm not trying to make it complicated, but realize the inverter gets its name from the type of electronics that we're actually using to control the compressor and the outdoor fan. Um, and you can see the outdoor fan there to the left of the screen, and to the right is where the compressor and everything sits in its housing. Okay. All right, so here's a parts and pieces that make up the heat pump, and it's worth having some understanding of what these things are. But we're going to start with the indoor unit, and we got electronic circuits. It has to talk to the heat pump, the outdoor unit, and they have to be on the same communication channel. So there usually is a black wire, black jacketed wires, I should say, that goes from the indoor unit to the outdoor unit. Talk a little bit more of those in the line sets here in a minute. We have a temperature sensor up on the head of the coil in the indoor unit. We have some filters. We'll talk about cleaning and stuff later. And we have a motor and a fan that basically causes it to move air over the system and down across the coil and provides you the heat or the cooling depending on what season we're playing with. Okay. The outdoor unit has a coil outside where we are passing refrigerant around to either pick up or reject heat, depending again what season we're playing in. The electronic circuits, and this is the inverter unit, and really the heart and soul of the electronics with this is all on the outdoor unit or the inverter. We have a fan that operates on a fake AC circuit that's really DC driven, and gives us the ability to modulate the fan along with modulating the compressor that we have. All right. And if you look at this diagram, it uses blue to light blue for the refrigerants. So the darker blue is liquid, where the lighter blue is vapor, to a light orange, which is warm vapor, but not quite hot yet from the compressor. And that runs into a darker orange, which goes down to the compressor, and then it becomes a darker orange, even darker orange, leaving the compressor, and then out to the coil, and then rejects the heat out, and then turns back into a liquid. Okay, and those are the major components to this thing. Now, the head, there's a couple different options, and we'll talk about those here in a few minutes. And the outdoor unit is usually what's called a slim condensing coil unit. And by that I mean they're only about 18 inches deep. They're usually about, well, depending on the size of the capacity of these things, anywhere from about 40 inches wide to about 3 feet high, so 36 inches. Okay, they do get bigger, and I'll show you some pictures of those coming up right here. So the one on the left has the inverter unit where it's just a single condenser fan, and its job is to pull air in from behind the unit and bring it out through the front of the fan unit. So basically it's sucking air, outdoor air, through the heat exchanger and passing it out the front. The interesting thing with these is they take up a lot less room than the standard old air conditioning system of the past, and we can put them in places where they're a little tighter to deal with. Okay, the image on the right is another one. This one is one that has a larger condenser coil, but requires 2 fans to operate. So the one on the left is somewhere in the neighborhood of 3 to 4 tons, and the one on the right is 5 to 6 tons. Okay, and the ton I'll explain in a little bit, but just real quick, it's how we measure the heat capacity of refrigeration systems. Okay, in getting ready for this, I asked a lot of questions of people around the college. What do you want to know about heat pumps? And the one that kept coming up was startup cost, return on investment or ROI, and then the warranties. So I'm going to try and cover those briefly here for you. So first time cost, and I've got this from Forbes Home, and average installation cost is about $5,500. Okay, there are systems that will go as high as 10,000, but this isn't anything to be shocked about. The average hydronic boiler system using natural gas is going to cost you about the same price tag. All right, so it's not that big a deal when you compare heat pumps to traditional heating systems, and so on. It's going to change how you heat, but it's relatively the same. All right, so I'll give you a real example. An inverter unit that was purchased for $3,500 with heads costing $2,500 each on average. That's being said, some indoor units, the cassettes of the indoor units vary in size, so their prices change. Okay, but generally, this one was one that was installed in a house that I physically worked with. As an example, the 4-ton heat pump system had 5 indoor heads. The total installation cost for a house that was actually built in 1868, the heat pump was $16,500. Took 4 days in length for the all right. The installation took 4 days in length for the installers to complete this job. And the best way to say this is a house that has actually had a lot of renovations going on to air seal and insulate it. Okay, but still, it's an 1868 house. It's very typical of what you see in northern New York. Very few homes in our housing inventory are something that is very modern. Now, you get to a new construction where it's been built and air sealed, you can definitely bring this price tag down. Okay, but generally, I feel this is a very reasonable price tag for what's going on. All right, this was actually $11 per square foot in cost. Okay, so it's kind of useful to keep that in information because we're going to have to compare that with apples and not apples and oranges. So keep that in mind. All right, so a hydronic boiler system, to give you a cost comparison here, is 5,000 to 10,000 with no cooling systems involved, just pure heating. Okay, and that ranges from $10 to $25 a square foot. These systems have such nuances that it's difficult to get an exact cost. And by that, I really want to describe this as you can take an existing heating system that is a hydronic system and put a new boiler in for about $5,000. But if you have to do the infin tube, and that's the heat exchanger that goes around the baseboard, sometimes referred to as baseboard heating, that is going to cost you extra money. And the other bit is, as you start tightening up the house, you can find out that you have more heating capacity than you need. So things change. You add an addition on a house, you can add more need for heating capacity than you have. So I can't really tell you there's an exact way to process this because number of fittings, the number of length of copper pipe that has to run around the system, all that's going to play into to make this have such nuances that it's not going to be an easy way to compare this, okay? But generally, $10 to $25 per square foot. All right, radiant floor heating. More and more homes in the northern New York area are doing radiant floor heating, and the average 2,000 square foot home is $28,000. That gives you a price comparison of $14 per square foot. So we went from a heat pump in the real system that I worked with, $11 per square foot, to $10 to $25 for hydronic heating, and $14 a square foot for radiant floor heating. Radiant floor heating, by the way, can be retrofitted into an older house. It's difficult to do. That's going to raise your price, but most of radiant heating is going into new construction. Okay, and it's easier to install it in a brand new house than it is to retrofit it to an old house through a renovation project. All right, let's talk about return on investment. And this comes from sourceheatpump.com, but generally 10 years is the average return on investment on a project of this nature, and the average lifespan is about 20 years. So you're going to get 10 years of profit from it, or 10 years of savings, depending on how you're going to look at it, and 10 years that you're going to have to pay off the investment that you made. Okay. When you compare it to electric heat, though, it's going to save you $459 per year. And I like this comparison from the standpoint that electric heat is the primary, I'll say electric heat. The electricity is the primary driver of a heat pump. So yes, we're going to use more electricity in the operation of this heat pump. But when you compare it to an electric heating system, you're going to save quite a bit of money per year. Now, how does that compare to a oil furnace? And if you take a look at that, we're almost $950 annually is going to be saved when you're replacing a forced air oil furnace with a heat pump system. Okay, and that's an average, believe it or not, of things that are going on in the northern New York area. There is natural gas. We have plenty of it and access to it, but we don't always have it in the right locations. So we wind up using fuel oil. Why do we use fuel oil? It's because it's easier to transport. The interesting thing is if you get rid of the transportation and start looking at the systems on their own, they all do their job very well. But it's the ancillary cost of getting the fuel moved to the site. So natural gas, we got to pipe through piping systems underground, and it's got to be something that the utility wants to put in order for you to have access to it. If you don't have access to natural gas, your other two choices for home heating are fuel oil, which comes on a truck, and you usually have a fuel tank in your basement or outside, depending on which way your house is set up, that holds a capacity of 275 gallons. They will usually deliver 200 gallons and leave some room in there, but you're going to have multiple truckloads come during the winter. If you don't use that and you want to use propane, again, you buy a tank, it's outdoors, they deliver, and they keep bringing you propane every so often. Okay. Now, if you take a look at a heat pump, we actually just tie it into our electrical systems in our building. Our homes have it. The utilities provide it. You can do this with renewable energy sources, so you could do wind or solar and add this to your load for your house and get your electricity that way. But primary electricity is a very clean and energy efficient way to move the fuel source for the heat pump around. Okay, and I'm trying to use that word cautiously. I don't want you to think of electricity as fuel, but it is the energy source. Same as fuel oil is an energy source that provides the furnace or the boiler system in your house the um, energy it needs to provide you the heat that you want. Okay. All right. Um, that got way off from return on investment, but generally, it's not a easy process to look at return on investment. It's complicated. Next question that the people I asked wanted to know about warranties. So in general, it varies. Each manufacturer has confidence in the materials that they produce, and they will warranty it as long as they know that they're not going to have problems with it down the road. On average, most of them are providing 10-year warranties on things. If you get into commercial systems, they get a little fussier. They'll use 5 and 7 years, but most of them are providing 10-year warranties as a bottom line. The real system that I referred to as the example from a real home here in northern New York is a Daikin heat pump system, and it has 12 years warranty on the indoor unit parts and 10 years on the inverter and compressor replacement. Okay, which is pretty good. Um, Most of the things that are going to go bad are going to go bad down the road. They're not going to go bad immediately. If they do go bad, it's because the installers did something bad or forgot to do something or some other crazy thing happened. And they're prone to everything else. Mice, rats, chipmunks. Hopefully, you don't have a raccoon in your house. Red squirrels can chew on things and get into trouble and cause you lots of problems down the road. Okay. Um, the good news is it's all fixable. Okay. But it's not any different than if it was your heating system that was the existing stuff, the furnace, the hydronic system. Things still chew on wires. All right. But generally, the warranty is pretty good. Remember, the lifespan on these systems is about 20 years. So you can go 10 years pretty confidently. In this case, the inverter unit from Daikin is going to got a 12-year warranty, and I would venture to say that those compressors and everything else in there is going to operate very well if they're properly taken care of all the way through their 20-year lifespan. Okay. All right, maintenance and service. So a couple things that you should know as a owner of a heat pump is how to maintain it. It doesn't take much, um, but it is one of those things you should put a mark on the calendar and you got to go do it. Okay. So indoor units usually have reusable filters. You should clean these every 4 to 12 weeks, and it really depends on the use. The ones in my own personal house, a couple ones we use quite heavily in different places in the house, definitely every 4 weeks. I have a couple that don't get used except normally during the summer, and are the indoor units. I mean, don't get used until the summer when it's cooling season. And those can go 12 weeks in the winter, and I don't have to worry too much about it. It depends on how often you're using it. Okay, so keep that in mind. But it wouldn't hurt every 4 weeks. Pull the filter out, and there's a little door, and I'm going to show you a picture here in the next slide. Basically, you lift the filter up out of there, take it out, do a little vacuum job on it, clean off any dust and other things that have collected on it, and then mild soap and water. Um, so a little uh, dish detergent, but diluted really thin. You don't need a lot of it, and warm water and a soft brush, and you can clean these up very well. Okay, then let them dry. The actual instructions say place in a sunny location. I don't know about you, but placing a filter outdoors in the sun in the wintertime is not my cup of tea. First of all, they won't dry, they'll freeze. Um, so you're going to have to find some place where you can let them drip dry. And once they're dry, you can put them back in. Okay. Uh, Basically, don't use a hair dryer though, because they are a plastic material and you'll wind up melting them or fusing them together, and then you're going to have to get new filters. Okay. But these are really reusable. Keep in mind they are fragile, so don't get too heavy with the brush. But you can clean them up and then stick them back in once they're dry. Okay. And the next picture shows you one of the heads in my house. So the indoor unit looks like this. And if I flip the front lid open, you will see that I have removed one of the reusable filters. And that is all there is to it. There's some cleaning that should go on with the coil inside, but if that gets really filthy, you probably want to call a service technician. Okay, but if you take care of these reusable filters, the coils themselves should never get dirty. Okay, so keep that in mind. Doesn't mean that you shouldn't take a little more care every once in a while and have a service tech come in and do a quick maintenance on the coil itself, but there are no ways the average homeowner can get in and clean that coil without having some special tools. Okay. All right. The inverter cleaning. Um, you should clean this by using a again, mild detergent from the inside out. So you're going to have to take the, well, I don't want to say this. You have to take the cover off the fan, and you're going to have to spray the coil from the inside of the unit and push all the debris outside. All right, so basically off the coil fins that are outdoors. Okay. And what I'm talking about is it can pick up leaves, it can pick up grass clippings, it can pick up spiders and all kinds of fun things that you just would never expect. But because the fan's pulling air through there, it's anything that's in the airstream is coming with it. It's going to get stuck on the coil. So that's why we blow it outward with soap and water. And ideally, if you're really good at this, I'd say you could do it, but I'm going to ask you to call a professional. As a professional engineer and someone who teaches heating and ventilation and refrigeration systems, I can do this because I've done it a number of times. But if you've never done this, this is worth your service call once a year. And while you got them here, have them check the indoor units, make sure they're all operating properly, and you're going to be a lot happier. And if your HVAC contractor is worth their weight in gold, they will actually ask you to come do an annual service on it. And you're going to want them to do that, and it won't cost you a lot, but you want to maintain your system. Okay. Yeah, the last line, my advice, ask a professional. Don't try to do this outdoors. Professionals come with the right tools and the right supplies. And cleaning a coil outdoors it's a messy process. Cleaning the coil indoors is a messy process. But from the indoor unit, you can easily just pull those reusable filters out, follow the instructions, and you'll be fine. The inverter unit, please ask for some help. Okay. All right, here's a picture of a service tech. Now, interesting with this, he's got the cover off this Panasonic heat pump. And this inverter unit, you see the circuits that are in there. You see the compressor hiding in there. I can see the not the TXV. I can see the reversing valve. And while they're there, they're checking all the other stuff that goes on with the inverter. So it's worth having to do that. But you see, he's basically pulled the grill off the fan to get access to the indoor coil. And he could, if he wanted to, where he's got some of his tools laying on the top, he could easily pull that top off and then be able to spray down in there. The interesting thing is once you get this grill off the front of the fan, you can easily get access to the inside of the coil and use a hand pump pressure bottle and basically blow that stuff away. We don't use pressure washers because that's damages the fins on the coil. But we want to get in there with some special coil cleaner, and it'll dissolve all the grease and dirt and anything else that's in the way and blow it out. Okay. All right, we have multiple options when it comes to the indoor units or the cassette, and I'm going to show those to you. All right, so we're going to go through each of these individually. I have a Daikin system, so that's why I chose Daikin, but you don't have to have that one. But they all pretty much come the same way. So wall hung units. And I showed you an example of the Daikin wall hung that's in mine. Go back and look at that. Truthfully, they are for retrofitting to a existing house. They're there, they're visible. I'm not going to lie to you. But the majority of them, once you get them installed, they kind of blend in and you forget them. So the reason these are designed this way is it's minimal um, intrusion into your space, and it only requires a 1.5-inch hole that the inverter covers up, and they run the line set and the communication cable back down through to get it to the outdoor unit. And then they should, if they do this right, seal up all the air gaps between any penetrations they've made through a wall, because again, we want to keep the house air sealed as much as we can. The easy part is they're relatively easy to hang. It's almost like hanging a picture. You want to get them level, and you need to have enough anchor points to hold it up. But they're not really heavy. One person can lift it up in place and get it hung up, and doesn't require a lot of extra help to do it. The location of these are usually placed someplace where they can either have immediate access to the outside wall of the house or to an inside wall that can be chased down to the basement, and then out the basement out to the inverter unit. Okay, so it's not always easy to figure out where to put these, and you should ask the contractor where they think they can get it, and then you and that person need to have a discussion if that's something you can live with. Okay, um, they're intrusive. I'm not going to lie to you about wall hung units. Okay, but the majority of it's planned properly. You can get them there. Okay, ceiling mounted. So this is primary for new construction. These fit between the um, joists of the ceiling, and they have very little that protrudes into the living space. You're going to see a set of diffusers that look more like a commercial diffuser system, but generally they fit really neatly. And again, other than remembering that they're less intrusive than the wall hung units. Okay, and yeah, the last line there, they do look a little commercially, um, but it's not a bad thing. They work really well. This particular one that I got shown here has diffusers on all four sides, so it's actually going to diffuse air all around the room, which makes your life simple because you only need to have one of them in there. Okay. Floor mounted units. So this kind of goes back to the old days of steam heating systems where we had radiators sat on the floor, and the piping came up to them, and the steam went into the radiator, and liquid water went back to the boiler. Okay. Um, Very doable, but again, you're going to have the floor space in the wall area to get them set up. But again, they're easy to install, and they only require routing of the refrigerant lines and the power to out to the outdoor unit. Okay, um, so it's an option. All right, duct installed. This one is probably the very less intrusive one of all of them. Okay, is a way to put that. So as long as we can install this cassette into some established ductwork, um, this will do its job really well. But it does require to have a duct that is able to push the air around to get it. Now, there's a downside to this because most duct systems are in the northern New York area are round duct, and it is usually left over from very old furnaces and no one ever changed them out. If you look at the shape of this thing, we are a rectangular shape. Okay, so in order to get this into operation, we are probably going to have to modify the duct and make some improvements to the air distribution of the house. Okay, again, that's going to raise your cost. In the long run, you'll have a much better operating system by doing this. Okay, and you can have less of these involved because your duct system is usually zoned to get air into all the right places inside your whole building. Okay. All right, how do we size these systems? This is not as easy as it sounds for the average person, but it is not overly complicated for the professional. Okay. So first thing we got to do is we got to start with a heat load calculation. And what we're really interested in is how much energy transfers across your walls, your ceiling, and your foundation of your home. And in order to do that, we use the ACCA Manual J standard to perform the heat load. It's a very precise calculation, and it really can only be done by someone who's been trained to do it. Your contractor that's putting this in should do it for you. If they don't do it, ask them, and if they him and haw about it, go get another contractor. Okay, or call a professional engineer that knows how to do these heat load calculations and ask them to do it. It's something that is really easy for a professional to do. And here's an example. This is one I've performed, I don't know, many years ago, I guess, on a particular house. And this was a summary of the whole house. So this isn't a room by room, but normally I would calculate the energy transfer from the indoor space to the outdoor space, room by room, because I'm going to look at what my zones are, and I'm going to try and size my indoor units to match my zones or the spaces that you're living in. Okay, so it's important to do it that way. If you ever need some help, don't hesitate to call us. College always loves a challenge for students to work on, and this is one of those things that we can have them do. Okay, but generally we're looking at this. We need to know the volume of the building. We need to know the area of the floor, the ceiling, the area of the walls, and then we're going to measure the areas of the windows and the doors and anything else that's going to allow energy to transfer from indoors to outdoors or outdoors to indoors. And it depends on the season. Okay, so the easiest way to qualify that is we do one for cooling and we do one for heating. Okay. And then we take a look at your leakage rate on the house, and the best way to do that one is to have a blower door done where we depressurize the house, and we can figure out where the air leaks are. Once we know that, we can give you an exact amount of air exchanges that should happen on that. And we'd really like to see an air exchange rate for a house where it's 0.2 to about 0.35. Okay, that's a relatively tight house. We don't want to make them too tight, but yet the tighter the better. And then we bring in intentional fresh air through a heat recovery system. Okay, and by that I'm talking about we want to bring in clean fresh air. Houses that leak in the what's classified as the infiltration rate is the amount of air that has to come in from outside into the space, and it doesn't come through the nice places. It comes through nooks and crannies, around windows, around doors, cracks in the foundation, through wall cavities because there's poor insulation in there. And I don't mean to gross anybody out, so hopefully you didn't eat your last meal just recently. But why do you want to breathe air that has walked its way through your outside siding, your insulation, places where the mice have probably run over the last 50 years, in through the sheetrock, past the paint, into the space through your carpet, and into your breathing environment? It's better to have a tight wall and have less air infiltration and then bring in intentional fresh air so that you're able to breathe clean, fresh air. Okay, so infiltration is a measure of unwanted air that's not through clean passageways. Okay, um, and there's a really great word used in the building science as interstitial spaces. That is spaces that are between the walls. Okay, um, it is notorious when I do energy audits on houses that I can always find interstitial passages that bring air from the basement upstairs, air spaces that go from outside to inside, and then vice versa. So in the wintertime, I can do exfiltration, which is warm air going outdoors. Now, when you open a door in the wintertime, of course, that all goes outdoors. Well, not all of it. We like to shut it quickly, but there's some air that exchanges out. The real thing with this is in a nice energy efficient home, I don't want to have to pass heated air outdoors. It's not our goal to heat the environment. And we just want to keep the indoor environment heated and the outdoor environment let Mother Nature take care of. Okay. So, but we want to use our energy efficiently. That's what a heat load calculation performs for us. Okay. It turns in the science of energy moving through spaces into a mathematical set of equations that we get an answer to. So back to my heat load calculation here. The infiltration loss in this house was 6,890, so 6,890 BTUs per hour. The whole heating for this particular house, I know this is room heating, but this was a total heating for this building was 20,975 BTUs per hour. Okay. This is a fairly well insulated house when I did this one. Okay. Um, and actually, I think this generally might have been a addition to this house, which is why it's probably set up this way if I remember this particular project that I worked on. But we're looking at the U value or the inverse of the R value, which is like the insulation value. The resistance to energy flow is the U. Okay. The area and then our temperature difference. In this case, it's 87 degrees. And we like to pick our design temperature for Northern New York. Depends on which part of the energy code you're looking at, and also in Northern New York, really which part of the region you're in. So Canton is minus 9 degrees Fahrenheit is the design outdoor temperature, and we like to design indoor for 72. Okay. The places in Saranac Lake, you're going to have a much lower outdoor temperature in the wintertime. So for your heating stuff, this number is going to change. Okay. And then elsewhere around the northern New York area, we can find different temperatures. Again, this is why you need a professional to do this. I know what I'm looking for when I'm kind of picking those outdoor design temperatures, and then we're going to go from there. Okay, so I do the walls. I take a look at windows, and windows have a different resistance to heat passing through them, so I got to account for those differently than I did your walls. I want to look at doors, and then I'm looking at the area for this, and then I got this ceiling that if it's on the ceiling that is connected to the roof, that's the one I'm interested in. If it's a two-story building, I'm not so interested in the heat that moves from the living room, let's say, to a upstairs bedroom above it. Okay, as long as the outside wall is completely insulated and sealed. Energy moving with inside the structure, I don't care. Um, yeah, you might, but there's no reason to get paranoid about it. It's still within your building envelope, and that's the interesting part. All right. Then we have floors, and I do remember this one now. This was a um, insulated slab on grade, and we are accounting for the insulation around the concrete floor that was in there. Okay. Anyways, when we get all done, we get our total heat load, and that's the number we're designing to. So, cool thing, 20,000 is a little over a ton. Um, well, not a little over. It's almost 2 ton, but it's a ton is 12,000 BTUs per hour, and this one's 20,000. Okay. All right, so here is the meaning of a BTU per hour. So those who've been waiting long for this one, it's simply this. It's the amount of energy that's transferred per hour. Okay, so a BTU, a British thermal unit, is what we like to use. Europe and even some places in Canada use watts, and watt is equivalent to a BTU, or BTU is equivalent to a watt with some conversions. Okay, but generally a BTU is, take one of those wooden kitchen matches you've ever played with, um, and that is the amount of energy that is contained within that one wooden kitchen match. Okay. The proper definition is the energy it takes to raise 1 pound of water 1 degree Fahrenheit, and that's how we got British thermal units. Okay. A ton is the energy it takes to melt 1 ton of ice in a 24-hour period. So 1 ton equals 12,000 BTUs per hour. Okay. And we can thank Willis Carrier for that, of the Carrier Corporation. But that is how we actually classify that, and that's generally what that's about. So if I take my, let's get a calculator out here real quick, and I had calculator, come on, 20,495 divided by 12,000. I got a 1.7 ton refrigeration load, or heat pump, or air conditioning load. So I'd wind up putting a 2-ton system in just to satisfy that particular heat load that I gave you back in the last slide. Okay, so heat loads are done by professionals, and your contractor is qualified to do it. If they've been trained in it, ask them, and you should be good. All right, let's move on to rebates and incentives, and we're slowly coming to the end of this. I'm going to make this real simple. Okay, the best way to deal with this is go to cleanheatnewyork.gov. All right, and they will give you a list of available rebates, and the same for financing options. Okay, but generally, New York State is trying to move to a greener heating system and eliminate the fossil fuel use. There's some concern across the North Country, and you're going to have to work on changing minds. But the state of New York is not coming to take away your furnace. If you heat with oil, you're going to be able to continue to heat with oil, but eventually no new oil furnaces will be sold, or hydronic boilers. And that is to reduce fossil fuel consumption. Okay, and we are moving to an electric economy for New York State. So it's going to take a while. It's not going to happen overnight. As much as anybody that's trying to instill fear in the general public, it's not going to happen overnight, and they're not coming to take your old heating system away. Now, I will ask you to have your heating system evaluated and see if it is time to have it replaced. I have seen a lot of heating systems in my lifetime. Some of them scare me to the standpoint, well, they work, but they retrofitted a very old unit with a system that was probably a coal fire furnace with a fuel oil gun, and they were still using it. And it's like, this system just needs to go away. You need to replace this and get a more modern one. Okay, it's the same thing happening now as we're moving to heat pumps. They are becoming cleaner and more efficient. And why do we want to live with a heating system that is less efficient than a heat pump? Okay. And I said, I'll promise you, I will get a slide done on efficiencies, or not a slide, a presentation done on efficiencies. But anyways, for rebates and finances, best place is Clean Heat New York. Go look it up. All right. So New York State is trying to switch to an all-electric economy and or reduction of fossil fuels. Okay. And this is a statement from the governor's office, and I pretty much going to use it verbatim. But Governor Hochul is asking us to improve the air quality and reduce emissions. So combustion puts things into the air that you probably don't want to breathe. No heating system that uses fossil fuels can actually be very clean. All right. So those that burn wood, yes, it's a great heat source. They're only about 60% efficient. Well, I take that back. They're only about 40% efficient. And when they don't burn in a very low moisture content wood, you don't get complete combustion. And you're going to wind up with all kinds of tarry substances sticking to the inside of your chimney. It could cause chimney fires, but even let alone if it is burning properly, there's still a lot of combustion that's going up the chimney that isn't complete. And we're going to wind up causing problems for people in the local area when they're breathing. So it's time to change, time to improve our air quality. I have done a bunch of research with pellet heating systems. I'm a fan of wood pellet systems, don't get me wrong, but again, there's still a combustion process that's using wood matter to provide heat. Okay. Fuel oil systems are 80% efficient, so you're not getting all of it out of that, all the energy content you can. And then natural gas, we can actually operate natural gas up into 95 to 96% efficient. Okay. Electricity is still more efficient than all of that, though. So, and the reason you think about this is it's the density of the fuel. So firewood is a large, chunky fuel source. Okay, comes on a dump truck. They dump it out. You throw it in the wood stove, and you heat your systems with it. Wood pellets come pelletized, which makes the density smaller, and we get 40-pound bags that have all the energy content of 7,280 BTUs per pound, and does it in 40-pound bags. Well, that's the same energy content that's in cordwood, but the size is much larger in cordwood. Okay, and then if we move to fuel oil, we're at, I'm going to use a ballpark number here, 140,000 BTUs per gallon, and natural gas is 100,000 BTUs per cubic foot. Yeah, I'm going to stick with that number. I may have said that wrong. On the next recording of this, I may want to change that. All right. So anyways, here's the guidance that the governor's put out. We'd like zero emissions in new construction with no on-site fossil fuel combustion by 2025 for the new constructions. Okay. For smaller buildings. So residents, homes, that sort of stuff. By 2028 for larger buildings. The change to do this is readily available. We don't need to have fossil fuel systems in these. We've been talking about heat pumps here, primarily air source heat pumps, but on commercial buildings we can do geothermal systems, even more efficient. I'm a real personal fan of geothermal systems. For residential applications, not so much given the housing stock. Unless it's a brand new construction, you're not going to find that geothermal is a cost-effective way to switch up. Okay, um, save that for another video too. All right, so she's proposing that New York State takes the lead in prohibiting the sale of new fossil fuel heating systems by 2030. Okay, for smaller buildings, and then by 2035 for larger buildings. Okay, it's easy to change our heating systems when we do it ever so slowly and do it in a methodical and well thought out way. New construction, it's easy. Choose a different heat source. Okay, electricity, heat pumps are a great way to go. Okay, if everybody could afford electric heat, that would be too, but it's not. Um, and I will say this one thing on heat pumps before it's an efficiency thing. I'll save it for that, but I'll bring it in here right now. Heat pumps are, I don't want to phrase this without giving all the people craziness, um, are 3 times more efficient than the energy we put into them. And you're laughing at me, I'm hoping, because it's really hard to have anything more than 100% efficient. Okay, but for the amount of electricity we put in the system, we get 3 times the energy output. Now, how do we do that? Well, that is the thermodynamic principles of refrigerant as a liquid going to a vapor, and then the compressor using some electricity to compress that into smaller packets at high pressure and higher temperature, and then rejecting that heat into the space we want it to be rejected to. That's where that coefficient of performance is what we actually call it, of 3 and higher becomes part of that. Okay. If you look at a window unit for just general air conditioning, you're going to see something called a SEER, SEER, or seasonal electric energy rating. Okay, and they're in the 20s. That's just a different version of this coefficient of performance. And that's how we sell things to the public. We sell them bigger numbers is better. And in order to do that, we mix apples and oranges to come up with that number, where the coefficient of performance is BTU in, or BTU out divided by BTUs per hour in. That is the true mathematical equation of how to do things. With the SEER ratings, we're providing the output in BTUs and our input in watts. Okay, so we wind up having 2 different numbers. So not a very good engineering approach, let's put it that way. Okay. All right, anyway, so that's my kick on efficiency. Why we can actually do the second bullet point here is because we have very efficient options to change to. Okay. And then the idea of this is to help building managers make informed choices and cut their electricity bills and their emissions. Okay. Unlike electric heat, a electric heat pump gets more energy delivered than what it actually consumes. Okay. All right. Other concerns? I'll leave these for some real simple things here, but you don't want to put the inverter unit someplace where there's going to be prone to flooding. Okay. There is a lot of electronics in there. Yes, it's meant for the outdoor environment. They're sealed up so that they can't get stuff in there. But floods, it would not be a cool thing to have these things sitting on the ground and have them get flooded and saturate the electronics in them. Okay. So usually you want them up off the ground so that they are there. Heat pumps can be noisy, and the noise level is 50 decibels. So I mean, if you talk about that, it's a little about the same level that I'm talking at, and you hear it. Okay, if the heat pump, the inverter unit is attached to the sidewall of your house, you will hear it, but it's low enough that it's a background noise. It's not loud and obtrusive like the lawnmower is intrusive. Okay, you can hear the lawnmower, you know it's there. A heat pump, um, the average person doesn't even know it's there and forgets about it. Um, I'm a geek. I know when my heat pump's on. I know what I'm listening for. Um, so if you're attuned to it, you're going to hear it come on and when it cycles off. Okay, but the majority of the people won't even notice that it's on. Okay, um, remote controls. The little controller that comes with the heat pump unit is not um, a thermostat. It's an on and off switch. It's a remote control, just like your TV has a remote control to turn it on and change channels. Okay, and that's really all it does. Now, I will say this about the remotes. The automatic mode on the remotes should be not used at all. Um, Energy Vermont actually puts this out as a statement to the public in Vermont, and it's the best statement I've heard to go with this. Set the fan speed on the indoor unit at the level that you can tolerate as background noise, but not fast enough to make you want to turn it down all the time. And then set your temperature where you'd like to have it be that's comfortable. It will take you some adjustment to get used to what that number should be, but generally what you're going to find is set it and forget it. Set the fan speed and set your temperature, and then forget it and put the remote someplace where you can get to it if you need it, but don't go constantly changing it up and down. They don't work like your wall thermostat for your hydronic system or your furnace, where if you're cold, you crank it up. These actually work on a longer, consistent cycle. So once you set it, the best thing to do is forget it. Okay. And there are times, when it's cold, you're going to want to change the temperature and you may want to change the fan speed. The interesting thing is these systems are very smart. They tend to, through the inverter unit and the computer systems that are on board with this, to measure temperatures all over the place on the indoor unit. On the outdoor unit, it has multiple temperature sensors, and it's making adjustments to things based on what it's been programmed to do. Okay, so if a space is cold, it will ramp up the compressor, ramp up the outdoor fan, and send a signal to the invert or the indoor unit that we're actually going to put some more heat into you. All right, so that's kind of that stuff. All right, there are times where backup heat is advisable. Okay, I said that the temperatures that these things operate down to minus 20 are reliable and they still provide heat. But there are times still in northern New York where we're going to have minus 30-degree days. And yes, they will heat at minus 30. Minus 27 is the temperature that it boils off at. So that's really our lower limit of 410A. But at minus 27, we're basically heating it with electric heat, driving the compressor, and there's very little energy transfer going on with the refrigerant. Okay, we want a delta T, or a difference in temperature, that causes energy to transfer from one place to another and affect the phases of the refrigerant from liquid to a vapor. Okay, so there are times we're having electric backup heat in the heat pump system as a good idea. Okay, I don't want to advocate for this because it's not where we're going with the economy, but having a furnace that is backup would be a good safety net, but something that eventually you want to phase away because we want to get away from the fossil fuel systems. And the chances are, if you're at this point, or a professional has told you that this heating system of yours is at its end of life, you probably want to get rid of it anyways. Okay, so don't keep around a system that is worn out, going to cost you money, and doesn't provide you reliable heat. Okay, there are other ways to provide backup heat. Um, in this particular case, electric heat with a heat pump system is probably reliable. You're only going to use the electric heat for hours in the heating season, not days or weeks. Um, so keep that in mind. Okay. All right. Longevity. These are really meant for 20 years. They're going to be around for a long time now. And the truth of the matter is, at 20 years, there's probably a new system that is more energy efficient and will operate with the newest technology, and we'll probably want to change these systems out at that point in time. Okay, so think of them as long term, but in 20 years, a lot of technology has changed um, just in my lifetime. All right, and it's going to change again, and it's going to change faster. Okay, so yeah, they'll last you 20 years. In 20 years, probably want to change it out. Okay, and I hope this has been a helpful and useful time. And I'd love your feedback. If you got questions, you can contact me at SUNY Canton and share your questions. I'd love to come up with some more videos that work on this stuff. Thank you, and have a good day. Oh, I guess I forgot to do my reference slide. My students would be very upset with me. So some of the pictures I got from freepix.com, I try to find as many images that are not copyrighted, and I appreciate all the images that somebody puts out that are not copyrighted. And then other places where we're doing it, we're not making a profit off this, so it's educational use. But from Daikin.com, and then Source Heat Pumps is where I got the reference for return on investment. New York State Clean Heat, it's a government website, and then Governor Hochul's news announcements from the governor's office. So enjoy, and you can go take a look at these websites, and there may be some other things you would really like to explore there. But again, thank you for your time, and let me have your feedback, and let me know what you'd like to have next.